So, Sushmita, I start at 10 o'clock.
Okay, so there will be some opening remarks. I
Okay,
just
okay.
start the workshop. I will say some things about the scope and the history of the workshop, and then we'll pass it on to you.
Yeah. So nice
So-
to see you after a long time. You should visit ISI, yeah?
Yes,
Okay.
I have not visited any place since all these
Yeah.
things started. Since actually the last edition of this workshop happened. So
Oh, yeah, I can understand.
sure. Thank you. So yeah. So we'll just start in 2 minutes, just to allow more people to come. So can you all check? Everybody can unmute themselves and ask questions if needed. It worked, we tested on a few of us, but still.
Hi.
Hi, Shamanta. Hi, Neil. Hi, everybody. Oh, hi, everybody. I see a lot of familiar names, but I'm just trying to scan and see.
But last edition of RTA happened at IIT Gandhinagar, right?
Right, 2020, right before the...
Right, for the pandemic, yeah. We also sneaked out to ISER Pune after that for PC 301, and I think that was the last trip that many of us had, I think, since.
Correct, exactly. So I couldn't make it to the RTA workshop in IIT Gandhinagar, but we met at Pune, right? So that was the before COVID era.
Right, yes. It's good to see that things are opening up again. So fingers crossed, really, hopefully. Yeah, hopefully this will happen in person soon, but.
Yeah. Hopefully. So this last year, we couldn't because of all the confusion, what would happen and how to do it. So this time we're like, okay, let's get going and we'll do it. And in the way that the rest of the world is operating over Zoom.
Yeah, and it's a great format. I think 9 tutorials is like, it's wonderful. So really looking forward to it, yeah.
So yeah, that is I'll slightly touch upon why we thought we needed to slightly change the format given the realities of working from home, and we couldn't be sure if now we are going back to work. It's not but at the time when we were planning, we didn't know how much that would be possible. So having fewer talks, maybe a little deeper dive and split into two would probably be a little more easier for people to catch on. Are we good to go? Should we start then?
Yes.
Okay. So good morning, everybody. Welcome to the Recent Trends in Algorithms 2022 workshop. We will start with the proceedings with a few words from Professor Venkatesh Raman. He will touch upon the history and the scope and the goal of the workshop. And then I'll just say a few things about the current format and what we expect from the next few days. And then we'll be off to the races. Over to you, Venkatesh.
Okay, thanks, Sushmita. So you can hear me, right? Yeah, whatever I was going to say, actually, Neil and Sushmita already shared in this informal discussion. So good morning, everyone. This is, I know, for those who are joining for the first time, this is actually part of the series of workshops which we started in 2019, thanks largely to Aritra Banik, I would say. It was to address this long felt need that there is a large algorithms community in the country, but spread all over. Some institutions have slightly larger number than others, particularly in newer IITs and NICERs. People are isolated. So the hope was that this will provide a forum for algorithms community to meet in an informal atmosphere, listen about latest exciting things happening, share their own work, find collaborators, and so on. So in 2019, Aritra Banik hosted it at NICER. 2020, Neil Dara and Manoj Gupta picked it up in IIT Gandhinagar. Last year, we had a discussion on having it in some form that did not happen for obvious reasons. And this year, Susmita, Vikram, and Aritra have again kindly agreed to organize this, though in a virtual mode. We will miss all the social atmosphere, but I realized that the registration the number of participants already has surpassed 2019 total registration. So this tells you some advantages of having it virtually as well, but I'm hoping that pretty soon we will meet physically. And with those few words, I hope you will enjoy this workshop. And over to you, Susmita.
Thank you. So as we were chit-chatting before the formal opening of the sessions, given the practical difficulties and difficulties or advantages of the way you see it of the online format, we slightly changed the sort of the way this workshop was held the first 2 times in nicer and all. In particular, we have fewer talks. We have 9 speakers, each of whom will have 2 sessions, 1 hour each. And the goal was to do a deeper dive into some really deep and areas of algorithm that are of contemporary interest. And that itself was not, finding those topics was itself not an easy task. It really tested our knowledge of what is important and what is trendy, what is of public interest, and so on and so forth. So, but at the end, it was a sort of, embarrassment of riches as to how many things we could choose from. And we are absolutely delighted by the panel of speakers that we have managed to assemble. We have talks on algorithms for big data, game theory, clustering, social choice theory, approximation algorithms, online algorithms, geometry, algorithms on parameterized problems, and so on. So anything that is sort of your interest, I'm sure you'll find, and you'll find things that maybe you were not aware of, and you'll be interested in hearing about them as well. To keep the talks accessible for everybody, and particularly our students who really are ideally our target audience, the first hour would be devoted to some background and basics on the topics. And the part 2 would be a more technical discussion on 1 or more problems. So with that, I want to say that the TCS group in IMSC is absolutely delighted to host you for this edition of Recent Trends in Algorithms. And thanks a lot to the highlight of this week, the speakers and our student participants. And they have, thrilled us by the level of, interest that they have shown, the number as reflected in the number of registrants and so on. And we are still getting requests as to allow more people to participate. So for having said all of that, I sort of transfer my responsibilities onto the chair. And so over to you, Arijit.
Thanks, Susmita. So it's like really a privilege to introduce the first speaker today, Arindam Khan, who is a faculty member at IISc. So Arindam was my 1-year junior in Kharagpur, and I'm delighted to see his progress in the wonderful work he has been doing over the years. So just to introduce Arindam, Arindam did his PhD from Georgia Tech, and he has been working mainly in theoretical computer science, but his work spans multiple areas of theoretical computer science. So he has been working in approximation algorithm, combinatorial optimization, online learning, online algorithms, and geometric algorithms, and many other areas. Okay, so his wonderful work has already been recognized with different awards and things. So I will just mention a few because the list is so long. He got the Best Paper Award. He and his co-authors got the Best Paper Award in International Symposium on Mathematical Foundations of Computer Science. In 2020, his work has appeared in Highlights of Algorithms. 2021, he got Pratiksha Trust Young Investigator Award, Google Explore CSR Award, and more recently, the Google India Research Award. Today, Arindam will be talking about his breakthrough result in for approximating independent set in intersection graph of rectangles. So Arindam, we are really looking forward to your talk.
Thanks a lot, Urjita, for the kind introduction, and Thanks a lot to the organizers for this invitation. So let me share my screen. And okay, is it visible, the screen?
Yes, I can see it.
Okay, so welcome everyone. So this talk is on approximation algorithms for maximum independent set of rectangles. And it's a joint work with 5 people: Waldo Galvez from TU Munich, Madhusudan Reddy, who was an undergrad at that time, third year undergrad from IIT Kharagpur, and now he has started in CMU as a PhD student; Matthew Mary from University of Warsaw, Poland; Tobias Momke from Germany; and Andreas Wiese. He was in Chile that time, but now he has moved to Netherlands. So in this talk, it's a 2-hour talk. So first hour, today actually I'll focus on the background, and I'll talk about other problems also in this area. And maybe at the end, I'll start talking about technical details of our result. And tomorrow it will be more technical. And please feel free to stop me at any point. I want to keep this as interactive as possible. So if you have any question, please feel free to ask me, stop me at any point and ask the question. So let's start. So we have, as I said, the talk is on approximation algorithms for maximum independent set of rectangles. So first I'll talk about approximation algorithms, then rectangles, and then maximum independent set. So it might be, most of you already know about approximation, but for those of you who do not know, just to define, approximation algorithms are efficient algorithms that find near optimal solution. And it's a very classical area in theoretical computer science. There are multiple textbooks. For example, this Smoish and Williamson or Vazirani's textbook is there. And the talk that I will talk about, it mainly focuses on geometric approximation, which is an intersection of approximation algorithm and computational geometry. And for that, the textbook by Sariel Harpelez and other resources are there. So an algorithm for a so it's an optimization problem can be minimization or maximization. The problem I will talk are mostly maximization, but in some related problems, I'll talk about minimization as well. So for a minimization problem, an algorithm A is alpha approximation. And this is called absolute approximation as well, because there is a notion of asymptotic, which will come later. If AI, which is the value of the solution of algorithm on instance I, is within alpha times opti, where opti is the value of the solution, optimal solution on instance I. And for maximization problem, I define an algorithm is alpha approximation if opt_i is less than or equal to alpha times AI for all input instances I. So there is a, normally people measure the approximation ratio by the ratio of opt_i by AI or opt_i by AI. So people try to make alpha. So in this talk, actually, I focus on alpha more than 1. So the definition is slightly changed, and that's why I kept this definition, that opt_i for a maximization problem is anyway more than AI. So we want AI to be as close to opt_i. So I want it is less than or equal to alpha times AI, and alpha should be as close to 1 as possible. And as I mentioned, this is called absolute approximation. There is another notion of asymptotic approximation. For minimization problem, that talks about the case when optimal solution is large. So this is the expression. So let me explain what is this saying. So just first focus on the things in the under this curly bracket. This is saying, okay, we're looking at the ratio of AI and opt_i and the maximum ratio there, given that opt_i is equal to n. So given a particular value of opt_i, I'm looking at all instances for which we get this particular value of opt_i, and looking at the worst case ratio of AI by opt_i. And then I look at the lim sup when n tends to infinity. So when n tends to infinity, what is the approximation guarantee that we get? So intuitively, that says that if I have alpha asymptotic approximation, then let's say AI is less than or equal to alpha times opt_i plus some small o of opt. So think of constant. If this kind of things happen, we call the algorithm to be alpha asymptotic approximation. Okay. So any questions so far about definition, because this is needed, the definition of approximation algorithm and so on.
Arindam, it like n tends to infinity, the value of opt tends to infinity here.
Yeah, so when n is not the number of items in this case, n is basically the value of optimal solution. So when opt tends to infinity, yeah, they're same. So opt I equal to n. So when optimal value tends to infinity, what is the approximation ratio that you get. That is called asymptotic. In the asymptotic setting, what is the approximation ratio? The reason it is considering the asymptotic setting is sometimes for some pathological instances, you can have maybe opt equal to 1 or 2, and then algorithm perform very bad. You need maybe 2 when opt equal to 1. So you get ratio 2. But maybe for large values, you also get opt plus 1. So then the ratio is much better compared to factor 2. Okay. Now, in this talk, I will talk a lot about PITAs, and there are several types of PITAs. So PITAs is polynomial time approximation scheme, and we call for a problem we call the problem is admitting a PITAs if for any constant epsilon, positive constant epsilon, there exists a polynomial time algorithm A epsilon such that A epsilon I is less than equal to 1 plus epsilon opt I. And the runtime depends on epsilon. So it could be n to the power function of epsilon. Think of n to the power 1 by epsilon, something. So if epsilon is a constant, then it is a polynomial time, n to the power constant. And this is saying that for any epsilon, you can get this. So you can get as arbitrarily close to opt as possible, but the runtime will increase as you get more and more closer to opt. So this is called PITAs. Now there is a variant called ePITAs, or efficient polynomial time approximation scheme. Then it is PITAs, but the runtime is slightly better. So now what you want the runtime to be order of function of epsilon times n to the power c. And here the exponent of n, the c, it is independent of epsilon. So think of an example of runtime, something like 1 by epsilon to the power 1 by epsilon times n to the power 100. That's a ePITAs kind of a runtime because the exponent is independent of epsilon. Then third one is called fully polynomial time approximation scheme, or fPITAs, when the runtime is polynomial in both n and 1 by epsilon. So think of 1 by epsilon square n cube, something like this. So ePITAs, fPITAs, and PITAs. And there is complexity theoretic relationship. So if you know a problem is APX hard, then it will not imply a PITAs. If a problem is W1 hard, assuming opt is the parameter, then it implies no ePITAs. And if a problem is strongly NP hard, it implies no fPITAs. Some more PITAs. So one is called asymptotic polynomial time approximation scheme. So it is PITAs, but in the asymptotic setting. So as I mentioned, the asymptotic ratio or approximation ratio becomes 1 plus epsilon. So this extra part, you can think of this as a small of opt as well. But for now, assume it's just constant. So it's a constant. So when opt is very large, opt tends to infinity, this constant is very small compared to opt. So you can ignore the constant, and the ratio you get is actually 1 plus epsilon. Then there is something called quasi-polynomial time approximation scheme, or QPITAs. So here we get 1 plus epsilon approximation. The runtime is quasi-polynomial. That is n to the power poly log n. So n to the power log n or n to the power log n square, something like that. And finally, there is something called pseudo-polynomial time approximation scheme, or pPITAs. This is again a PITAs, but not polynomial time runtime, but the runtime is pseudo-polynomial. So it's some n to the power constant, but n is the number of items and the numeric data that we have, it's polynomially bounded in n. So think of knapsack kind of problems. There's a numeric data, size of a knapsack or profit of a knapsack. That data, numeric data, it's polynomially bounded in n. So here I am assuming n to be the number of input items and the input, basically something like input. So there is a question. So QPITAs runtime. Oh yes. So QPITAs also depends on epsilon. So I did not mention. It is basically n to the power log n to the power order 1 epsilon. So basically the constant that we have here, you can have it a function of epsilon. So for constant epsilon, it will become a constant. So QPITAs also has dependency on the epsilon. And the advantage of QPITAs is if you want to show some problem admits PITAs, then QPITAs kind of shows that it implies the problem is not APX hard unless some complexity theoretic assumption like NP is subset of d time 2 to the power poly log n. So we kind of believe that if a problem admits QPITAs, it should also have PITAs. So to show it's not algorithmic, but kind of you believe if a problem admits QPTAs, you should get a PTAS. So any questions so far regarding the definition of PTAS, QPTAs, etc.? Okay. So now we'll talk about the second term, rectangles. So I know everyone knows rectangle, and in fact we love rectangles. So be it as financial K matter or
Arindam?
Yes.
Can you just go back to the previous slide once? Sorry.
Yes.
It implies it's not a PX hard. Okay, yeah, fine, got it.
So basically, we expect it to have a PTAS.
Yeah.
So yeah, we love rectangles from money to, let's say, flag to cricket pitch, etc. In fact, I mean, even in art, people like rectangles a lot. So some modern art examples are like this. So this figure is, its name is Suprematist Composition. This one is Blackfire, and they are sold like $90 million or something, the price. So even in arts, people like rectangles a lot. So in fact, people sometimes, so when scientists look for biomarkers or existence of life in exoplanets, they normally look for this oxygen level, because normally oxygen is a highly reactive element, and if you have oxygen in a planet, then that means there is something which is producing oxygen. There is some life there. But I'll say maybe rectangle is one of the biomarkers that we should look for, because you'll not find rectangle in nature, but for man-made structures, probably this is the most frequently occurring structure that we will see. So that's the reason like rectangles are so well studied even in mathematics and so on. So if you look at classical people in discrete math and theoretical computer science, many of them have studied this kind of rectangles or packing problems. So by packing problems, I mean placement of objects non-overlappingly under some constraints. I will define more formally later, but like Paul Edosh or Ron Graham, like Edosh started this area of probabilistic method, and Graham was the first person to give approximation algorithm, this scheduling problem, and even modern day greats like Terence Rao. All of these people are looking at this kind of rectangle packing, square packing kind of problem. There are dedicated websites which talks about packing things. For example, there is a website called Eric's Packing Center. If you search, you will go to this website. And this is only 5 examples I have here, but if you go to the website, there are I think 30 or 40 examples. So all types of permutation combination, triangles in squares packing, rectangles in rectangles, squares in squares, squares in rectangles, and so on. So all these different types of variants you have, and what is known for each of these cases, those things are there. So it's a very well studied area. So once I was watching a video by Eric Diman, and he mentioned one thing, that I think packing problems are appealing to mathematicians and computer scientists because they seem very simple, and the simplicity and elegance is kind of attracting many people. So you just need to place some items into container or some boxes and so on. But yet they tend to be extremely complicated to actually solve. So the elegance is the problem definition, but to solve them, actually you need a lot of sophisticated tools. So we're done with rectangles, and now finally I will start with maximum independent set. So independent set is a very classical problem, and independent set is a set of vertices in a graph such that no 2 vertices are adjacent. So for example, in this graph, the star graph, I can take either only the center vertex or the leaf vertices. Both are in independent sets. Similarly, we can take this hypercube graph, and there are many different independent. So in case of maximum independent set, or MIS, the goal is to find maximum sized independent set, because you can have different size independent set, and in this case, this will be the maximum size independent set. In the other graph, either this size 4 or this size 4, there are these 2 sets which correspond to maximum size independent set. So red vertices are the independent set in this figure. And this is a classical NP-hard problem. And one can see it's easy to get a trivial n approximation, because you can take just a isolated vertex. So n is number of vertices in the graph. So if you take just one vertex, it has no edges with any other vertices. So that means it's an independent set, a single vertex. And in the worst case, you can have it's a completely disconnected graph and there are n vertices. So you can have n vertex in the maximum independent set. So at least you are getting one, so you get n approximation. That is extremely trivial. But it turns out that is okay. And then you can slightly improve it further and you can get something like order n by log cube n. So this tilde notation is hiding some log n factor. But as you see, it's slightly better than n, but not a lot better. And it turns out you cannot really do much better. So there's a classical result by Hastad, which showed it's NPR to get even n to the power 1 minus epsilon approximation. Even n to the power 0.9999 is not possible if you assume NP is not subset of ZPP. There is slight improvement here in the hardness, but still, I mean, you see, it's still, you're nowhere close to getting a good approximation factor. So that's the present status for general maximum independent set problem. But we'll look at special graph classes for which this is easier to solve. So any question till now? As I said, please stop me at any point of time because we have 1 hour time today. I need it to be interactive and yeah, you can ask question anytime. Okay. So now we'll talk about this geometric intersection graph. It's a special type of graph. And here the nodes are corresponding to some geometric objects. You can think of polygons, spheres, disk, rectangle, etc. And if two objects overlap, then there's an edge between them. So think of a setting. It is an office space. It's an example I'm giving. Let's say COVID situation we have. So in this office cubicles, if someone sits, there is a radius of maybe 5 meters or 3 meters within which you don't want to enter because then there is a chance of contamination. So each of these chairs or cubicles, they are defining some kind of a disk region, and maybe it can have different disk sizes depending on the proximity to window or AC, etc. And then you can define this as an intersection graph. So objects are now disks, and if two disks intersect, you create an edge between them. So the graph will look like this. For example, these two disks, they are intersecting, so I create an edge between them. There are nodes corresponding to these two vertices. Similarly, for this, I create one node, and these two are intersecting, so I create an edge between them. So that's the way we create the graph. So it has both geometric interpretation as well as a graphical interpretation. And the goal is to find the maximum independent set in this geometric intersection graph. So from graph theoretic point of view, if you look at the graph, this is an independent set because none of the vertices are sharing any edge. Okay. These red vertices are defining an independent set. And in terms of geometric viewpoint, this is saying that the objects are non-overlapping. So there is a graphical viewpoint from independent set, and from geometric viewpoint, it says that objects are non-overlapping. Yeah, so this area actually is quite popular. So I was just few days back, I was just looking at DVLP, and I found in India, in last 10 years, probably there are 50 researchers who have published at least one paper related to this area, geometric intersection graph. So either in geometry or approximation or structural graph theory and so on. So it's a very popular object, at least in India. So recent trends of algorithms in India, at least it has been a recent trend to work on this area. So before going to complicated objects, I will start with the simple object of intervals. So think of the case when the nodes are corresponding to intervals. So there is an edge between two intervals if they are overlapping, and the goal is to find maximum independent set in this graph. And geometric viewpoint is finding the maximum cardinality non-overlapping intervals. Now this is so in this, for example, in this example, these are the intervals. So I drew it like a two-dimensional thing, but actually just to show the intervals. The first interval is between 0 to 3, second is between 1 to 4, and so on. And I can create nodes corresponding to each of this. So maybe this is the first one, second one. So I can create first node and second node. And if they're intersecting here in this region, so there is an edge between them. That's the way we create the graph. Now, this problem is solvable in polynomial time. So anyone remembers from undergrad algorithms, how do you solve these problems?
The algorithm.
Yeah, so greedy. So greedy says earliest finish time. So basically what you do, you start from the left and the first job that finishes, you take it and then remove all the other jobs that's overlapping with this job. Then again, you continue and the second job that finishes, you take it. And then again, you delete all the other intersecting job and then you continue. The third job that finishes, you take it and you delete the rest and continue. And then that will give you the set of intervals. And in this graph, you can see these three nodes are corresponding to the set of intervals. So greedy works in the unweighted case. Now, if we go to the weighted case, you can show the greedy does not work. You can probably take maybe a very high weight for this particular job that you removed and very smaller weight for this one. And then if you remove this job, you're already gone. So greedy will not work, but dynamic program works. So weighted case, how do you solve using dynamic program? So think of again the case when we have these intervals and now they have weights 3, 3, 5 and so on. And how do you solve it? So here the DP idea works on divide and conquer. So there are two types of DPs, but I will focus on the DP based on divide and conquer. So what we'll do is we can look at all these points and then I can divide this region into two regions, left and right. So whatever interval is cutting this straight line, I delete it. And the remaining portion I solve recursively, the left part and right part. So I can have many positions to consider. Maybe this one is one position, the second one could be another position, third one could be another position. And in this case, actually, I will delete both this and this because both are cut and so on. So what DP does is it tries out all possible such cuts. Now, how many possible cutting points are interesting? So it's only interesting to consider the left endpoint and right endpoint of these intervals. So there are n intervals, so there are 2n number of endpoints. You can actually only consider these 2n possible cuts and then look at the DP table for the left solution for the left portion and solution for the right portion and then patch and select the best solution among all of this. And that will already give you the optimal solution. So just think for 2 minutes maybe later and you will find out why this DP works. So our algorithm finally, the rectangle algorithm will be a generalization of this idea only. So I will again try to find some cuts and solve this problems recursively, the smaller problems recursively. Okay. Any question regarding this part? Okay. So now,
Arindam, just to get some more intuition. So so essentially you are guessing the cut, right?
Right.
I mean, you cannot just cut at the middle because that might be the wrong cut. So you are trying to guess the correct cut such that you can do the patching. That's what your DP will figure out, right?
Yes. So the point is, the guessing is not a difficult job because there are only 2n number of cuts that happen. So you just try out all possible cuts and DP table will still have polynomial size.
Right. But each level has n choices, right?
Okay. So how do you, let me write the DP then. So let's say the DP x1, x2, it contains the optimal solution in the range x1, x2. So let's say starting position was n and ending position is 2n. So I want to compute DP of 1, 2n. That is the final thing I want. And what I do is I look at the maximum over all I, and then I look at the solution of DP of 1, x plus DP of x, 2n.
I see.
Not it's I basically. 1, I and 1, so I is basically going from 1 to 2n.
Yeah.
And then I look into it, and when I look at this line I delete all this, I remove all the intervals that are intersecting this ith cut, and then I just look into the DP table, and you can construct it bottom up, this DP table.
Right. Yeah. Okay, fine. Thanks. Yeah.
Okay. So now we go to slightly complicated objects when you have squares. It's again quite simple. Actually, a simple greedy algorithm will give you 4 approximations. So normally it's a homework in approximation algorithm or computational geometry course. And the algorithm is as follows: that you sort the squares according to their sizes, and then select the smallest square, and then remove all the squares intersecting it and continue. And that already gives you a 4 approximation. And you can explain it in terms of relating something called piercing number with independence number, and then you can charge the corners of the rectangles for each of these points in each of the square in optimal solution. And this idea of squares can also be extended to other objects like disks and fat objects. By fat object, I mean object something like this, like it's a convex object. And if I look at the largest disk inscribing this object and smallest disk circumscribing the object, this ratio is constant. That's why it's kind of fat. So if I have an object like this, it is not fat because the ratio is really large, small and large, whereas a fat object will have square or disk or things which looks kind of not too thin. They are called fat objects. So most of these approaches actually extend to fat objects. And the reason maximum independence had become an important problem because it developed a lot of techniques for these problems, and those were useful for many other problems. For example, first Hobsbawm and Maass gave p-TUS for unit squares using a technique called shifted grid, which has been very useful in many problems. Then for arbitrary squares, even with weights, there are techniques called shifted hierarchical decomposition, which gives p-TUS, and then Timothy Chan also gave quad-tree-based algorithm, which gave p-TUS. And then there are geometric separator theorem similar to planar separator theorem, which again gave p-TUS for arbitrary squares. One can use local search algorithm for arbitrary squares and so on. So a lot of techniques developed around this area, and it was useful for many other problems as well, geometric set cover, geometric fitting set, and so on. So now we'll talk about rectangle. So one thing is for rectangle, many of these techniques don't extend because rectangle is not a fat object. It can be very skewed. The ratio between the width and height can be arbitrarily bad. So things like shifted grid or hierarchical decomposition or local search don't work, as we know, for rectangles. So we'll see only there are two main techniques which will work for rectangles. One is linear program, other one is dynamic program or separator theorem based dynamic program. So those of you who joined late, you can actually start from here. I will again define the problem that we are studying. So we're studying maximum independence of rectangles problem, and in short, I will call it MISR. And in this case, we are given a set of n axis parallel input rectangles. We are assuming axis parallel rectangles. There is one question. Do all of these works deal with squares or rectangles in 1 or 2 dimensions? No, most of these works that I talked about for squares, they can be extended to d-dimensional hypercubes as well. So if it is d-dimensional fat objects, it also extends. So think of cubes or 4-dimensional objects and other things are not really practical, but they have some application in database and so on. So yeah, they still work in those kind of objects. Yeah, so a set of n axis parallel input rectangles. So we are assuming axis parallel property here, and the goal is to find a set of non-overlapping rectangles of maximum coordinality. So in this example, I have 5 rectangles, and I can create 5 or 6, maybe six rectangles, and I can create corresponding graph as well. And the goal is to find independence in the graph or the maximum set of non-overlapping rectangle for rectangles. And this has many applications. For example, in map labeling, data mining, resource allocation. Think of a problem where this one dimension is like bandwidth, and another dimension is time duration. So now these job requests are asking for some amount of bandwidth for some time duration. So it's basically rectangles that you are getting, and your goal is to allocate maximum number of such rectangles. So okay, practical motivation is there, but as it's a talk in theory CS, why it's an important problem in theory CS? One of the reasons it's important because it has a lot of connections with other problems. But any questions so far about the problem of? Okay. So theoretical important ways. So there are this class of problems which I call bin packing type, and other one is knapsack type. And we're looking at packing problems. So our goal is to find some axis aligned non-overlapping placement. For now, as you only we're talking about rectangles. And depending on the rectangle's movement, you can define different problems. So in some problems, you can take a rectangle like this, and maybe you can move it anywhere, like vertically or horizontally. So that we'll see bin packing and knapsack are those kind of problems. In some problems, we'll only move vertically, but not horizontally. And sometimes we'll not allow any movement. So one question, can axis parallel constraint be waived? So I will talk about this later, but it seems it's very hard. So for example, if you just take line segments, one can, so I will talk about this later, but it's quite hard. For example, if you just take line segments, what we know is a simple two approximation algorithm. If you have axis parallel line segments, but which is a special case of axis parallel rectangles. But if you even take arbitrary line segment with any orientation, then the based on approximation is n to the power epsilon. So from 2, you go to n to the power epsilon. Even a poly n is not known. Even a poly log n is not known. So the reason is, if you have this arbitrary orientation, if you don't have the axis parallel property, then you can have much more complicated interaction between the objects, which is difficult to handle. So that's why people focus on axis parallel. So many of this can be extended to the setting where instead of only 2 orientation, so in axis parallel you have kind of 2 orientation basically. So the largest side of a rectangle is either vertical or horizontal. You can still extend to constant types of orientation, but extending it to arbitrary types of orientation is hard. It's difficult. Another reason people study axis parallel setting is because of the practical importance. For example, the motivation of MISR came from this bandwidth allocation kind of problem, and there it's exactly axis parallel. There are 2 resources, and basically the width is telling how much amount of resources it requires in one dimension, and the height is telling how much of the resources it requires in the other dimension. So that's why axis parallel is very well studied, and also in practice, many of these problems are coming from cutting problems as well, where you have some objects and you have to cut through machines. And in practical industry, people have this axis parallel cutting mechanism because it's easy to implement. So that's the reason axis parallel problems are more well studied. And also, if we don't have this constraint, it's very difficult. So at the end of the talk, I'll talk about the open problem. If we don't have this constraint, can we get even a polylog n approximation, log n to the 1000 or billion, if it's possible. But for rectangles, we'll show you can have much better ratio. You'll have actually a 2 plus epsilon approximation when you have axis parallel rectangles. Okay. So now let me talk about this slide and different problems with which MISR has connection. So in bin packing type problem, we have some rectangles. So in both these problems, we have some rectangles and we're going to pack them. And by packing, I mean it's a axis aligned non-overlapping placement. In bin packing problem, the goal is to pack all rectangles into minimum number of square bins. In knapsack problems, the goal is to pack maximum profit subset of rectangles into 1 unit square knapsack. So it's just like knapsack and bin packing classical problems, but instead of just unit bin, now we have unit square bin. Now, if you think of the case of 2-dimensional bin packing, then you have some rectangles. You want to pack them into unit square bins, but you can place rectangles anywhere you want. You can move it vertically or horizontally. And in this case, the based on approximation is 1.405, and we know the problem does not admit any epita, asymptotic polynomial time approximation. For 2-dimensional knapsack, the based on approximation, it's again similar, but you want to pack a subset of rectangles. You can move it anywhere and pack it into the knapsack. The based on approximation is 1.89, and we expect a pitas in this case. But yeah, so this is the 2 problems we have, and you can think, I mean, these are basically generalization of bin packing and knapsack. If you think of all rectangles have same height, exactly height equal to 1, then this is just this reduces to 1-dimensional bin packing or 1-dimensional knapsack. Then the other condition problem says that, okay, now the rectangles are fixed, their horizontal locations are fixed, but you can move them vertically. And then it's called unsplittable flow problem or storage allocation problem or round SAP problem, round UFP problem. So the problem is as follows. Let me talk about storage allocation or unsplittable flow problem. So it's a graph problem again. You have some path. Okay. It's not appearing for some reason. And then you have some jobs. And so this paths are saying, okay, maybe some time intervals and which job is from what time to what time. We are given some jobs and there is some profile, some capacity profile. So you want to schedule these jobs under this capacity profile such that, I mean, in that case, you can place the jobs, you can place it here or here or here, it's fine. So you can move it vertically, but the horizontal position is fixed. You cannot really move it. And the goal is to find a maximum profit subset of jobs, which you can fit like this. So it's a problem known as a storage allocation problem. And in unspreadable flow problem, it is similar, but you can also slice the rectangles. And you can, so there the goal is to, if you look at one particular edge, total amount of resource requirement by all the jobs placed in that edge should be at most the capacity of that edge. And this is again a very classical problem. I mean, in UFP alone, I think there are more than 20-35 papers in chalk soda. And very recently, this year only, there is a PTAS for this problem. And for storage allocation problem of SAP, there is a 1.69. So there is two variants. One is called uniform, where the capacity profile is uniform throughout the edges. So it's basically a rectangle type of object. But in the other case, you can have general profile, arbitrarily shaped profile on top. So for SAP, the best known result for general profile is 2 plus epsilon, and for uniform capacity, 1.69 is the 96 is the best known. And then there is a similar variant called round SAP or round UFP, where you want to find this kind of UFP packing of all jobs, but into minimum number of bins. And bins are this capacity profiles. And for this, there is a 2 plus epsilon approximation known, and there is the order log n approximation known for the general profile. And if you look at MISR, it is again a special case of this kind of problems where the rectangles are not allowed to be moved. So they are fixed. And now you want to find minimum number of bins where you can pack all the rectangles without any overlap. So that is rectangle coloring problem. In other words, you want to color the rectangle into minimum number of classes such that each color class are disjoint. And in the MWISR or weighted version of MISR, the goal is to find maximum profit subset of rectangles into one knapsack such that none of them are overlapping. So in this packing, the rectangles are fixed, so you cannot move them. And it turns out the techniques for one problem is kind of transferable to other problems in this area. For example, the log n approximation for MWISR, those kind of approaches have been used in the algorithm for round UFP or round SAP. Similarly, for even UFP PTAS algorithm, before that there is some other work which also use some special class of MISR instances to obtain improved approximation for UFP. Even for two-dimensional knapsack or two-dimensional strip packing, other packing problems, there's a technique for MISR which is called corridor decomposition, which was used to give improved approximation for these problems. And in turn, these two-dimensional knapsack algorithms were used to give better algorithms for two-dimensional bin packing and so on. So there's a connection between all these problems, and that made this MISR problem to be very important. So it has connection with many problems: two-dimensional bin packing, knapsack, strip packing, UFP, SAP, round UFP, round SAP, rectangle coloring, geometric set cover, geometric heating set. For example, some geometric separator-based approach for MISR was used to give improved approximation for geometric set cover problem for some particular objects. So that's one of the reasons MISR was so important. The techniques developed for MISR was useful for many other problems. And also it has deep connections with other areas like structural graph theory or discrete or commutative geometry. So I'll talk about this later, not today, but there is something called chromatic number and clique number of chi-bounded graphs. So chi-bounded graph means this ratio of chromatic number and clique number are bounded. And one can show that there is a linear program for MISR. Whatever integrality gap of the linear program is, that gives you a bound on this chromatic number and clique number ratio. So that gives you some structured properties for this structural graph theory. Similarly, we'll come across this Park-Tardosh conjecture, which is not dealing with really algorithms, but it's more a combinatorial question, and it has connections. So if you solve Park-Tardosh conjecture, it will imply an approximation algorithm for MISR and so on. So that's the reason MISR is theoretically so important. So any question regarding these problems or MISR till now? Okay. So now let's talk about MISR results. Oh, it's already almost 45 minutes, I guess. So the work of Khanna, I mean, there are multiple algorithms, log n algorithms known for the problem, 3-4 algorithms. And then actually there was improvement, and people showed you can actually get as close to log n as possible. I mean, this constant before log n can be made as small as possible. Then if you have Q to be the click size, then one can show 4Q, you can get an approximation of 4Q. Then Marx showed that even for squares, the problem is W1 hard. So we don't expect the epitas for this problem. And then Chalamsuk and Chuzai showed order log n algorithm using linear program. And we'll see this linear program later, maybe tomorrow. And then Adamus and Visa showed that this problem admits a Q-pitas in n to the power poly log n by epsilon time. There was further improvement by Chuzai and Na, and it was shown that you can actually get even better than Q-pitas. You can get poly log n time algorithm, n to the power poly log n time 1 per epsilon approximation. So people expect it should have a pitas because we have a Q-pitas for the problem. But till recently, log n was the best known algorithm. Even a constant was not known. So recent breakthrough by Mitchell first gave a 10 approximation. And it was a very surprising result. And the analysis was based on a lot of case analysis. So total 60 cases were there with some example of the cases. And it turns out, yeah, somehow it started with each of the cases and it worked out. It worked out. So it was like a thriller. But finally, all 60 cases are fine. And you can get it done. So the question was, can we get improved approximation, better runtime, and a simpler analysis, which does not go via so many case analysis? So what we showed is a polynomial time 2 plus epsilon approximation. So earlier there was a 3 approximation which was published in SOTA this year, but then there was an improvement subsequently, which was 2 plus epsilon approximation. And the high level idea is what we do is we show existence of a good structured solution. Now, in case of MISR, for example, the candidate solution, the candidate independent set solutions can be huge. You can have exponential number of possible solutions. All subsets of n items could be possible candidate. So that's exponential. So that's hard to deal with. So what we need is we want to get some kind of structured solution which is small in size, maybe n square or n cube or some polynomial in size. And this structured solution I can use as a good approximation of the candidate solution space C. So if I take any independent set in this set of candidate solution, then I can get a structured solution which is a subset of this independent set, but it is close enough. It's within alpha factor. So if I have this property, then what we'll do is we'll write a DP which finds the best structured solution. And structured solution, there are only polynomial number of candidates. So it can find the best structured solution. And then best structured solution is an alpha approximation of the candidate solution. So I'll get a good approximation of the original independent set. So the difficulty, so I'll show the DP-based algorithm, but it's quite simple. It's just extension of the previous DP-based algorithm that we talked about in the interval case. But that's quite simple. But the main difficulty is showing that, okay, how can you ensure you'll get a good structured solution? How do you prove that there is a good structured solution, and how do you find it? So even this good structured solution, existence of this may not be algorithmic. You can just show it existentially. There exists some solution because the DP will find it algorithmically. And it's also interesting because it's kind of tight what you are getting, this 2 plus epsilon, because even for line segments, the best known result is 2 approximation only. So think of axis parallel line segments and they're overlapping. So it's basically interval kind of setting, but now instead of only one direction, you can have both directions. So what you can do, how do you get a simple 2 approximation? You just take either vertical intervals or you take only horizontal intervals and then run the previous DP, for example. Then, or even the greedy algorithm in unweighted setting. That will already give you an optimal solution, and then you return the best of these two. That is giving you a 2 approximation. So even for axis parallel line segment, that is the best one, factor 2. And rectangle is much more complicated because much more complicated intersections can come in rectangles. And there we are getting 2 plus epsilon. So I believe to get beyond this, we need significantly new techniques now. So now I will go to the technical details, but it's a maybe how much time do I have? 5 minutes, 10 minutes, or?
No, I think you have more than 10 minutes. It started at like 5 minutes past 10.
Okay, so
You can go on to
11:05.
11:05 for sure.
Okay. So there is a question. Can you explain step 1 again? Yeah. So it's an NP-hard problem. The difficulty is because there are exponential number of possible candidate solutions. If you have n rectangles, possible number of candidate solution independent set could be any subset of this n elements. That's kind of exponential in nature. And if you want to go through all these solutions, that's too bad. You cannot do that. So what we want is, instead of so many candidate solution, can we get a small sized, polynomial sized set of solution S, which is a good approximation. That means, let's say I have, S has polynomial number of candidate solution, let's say n to the power 1000 or something. So if I have some independent solution which looks like this, okay, this is not independent actually, so maybe it looks like this. Maybe I can have a solution present in S which is very similar to this. Maybe I don't have this one, but I still have this two. So it's a good approximation, a subset of I, and it's within alpha factor. So maybe if I was 3 in this case, I prime is 2. So within 2 by 3 factor. So if I ensure S to have this property, that for any candidate solution, I can have a structured solution in S, which is close to the value of the independent set, then I'm done, because I can show there is a dynamic program which can find the best structured solution in S. And intuitively that is happening because the size of S is small. It's in polynomial. It's polynomial size. So DP intuitively can search over all these polynomial candidates in S and find the best solution. And that will give you the best structured solution. And as we know that if I take the optimal solution, that's also, there is a structured solution with an alpha factor of that, and we are returning the best structured solution. So at least it's better than that as well. So we are getting alpha approximation for the optimal solution. Okay, so now I have 10 minutes. I will not go over the technical part in detail. Maybe I will talk about guillotine cuts, one object, and tomorrow I will talk more about the algorithm for MISR. So I talked about the structured solution, but what do I mean by structured solution? So let me give one example, and that will motivate the next step. So the structured solution I'll talk about is called guillotine cuts. Now, guillotine cuts, it's an end-to-end cut along a straight line, which divides a rectangular piece into 2 smaller pieces. So when I talk about guillotine cuts, now it is not an MISR setting. It's an independent problem I'm talking about. And now we have some non-overlapping rectangles which are inscribed on some piece. And I want to separate them using this kind of guillotine cuts, which are end-to-end cuts along a straight line. And it's practically very relevant, and in cutting stock kind of problems this is studied. So you want to cut out some required geometric objects from some large source material like glass, rubber, metal, or cloth. So you think of these rectangular objects as some kind of pattern that you need for your purpose, but you want to cut them. And the cutting machines only can cut straight line way. You cannot really bend, because bending it's problematic in many of these cutting problems. And it's also easy to program this kind of guillotine. So there is column generation technique which is used in programming this. So this guillotine cuts was studied from 1970s by Gilmore Gomodi in the context of cutting stock. And because of it has lower cost in this cutting industry and simple usability. Now, what is guillotine cut? So we want this end-to-end cut, and we want a series of guillotine cuts, and each cut will separate a subpiece into 2 new subpieces. Like in this case, the original piece was P, and this cut is dividing into 2 regions, P1 and P2. And then once you have these regions, this P2, I can again cut it like this, an end-to-end cut, another guillotine cut, and then I can have another guillotine cut here, which cuts P1 and continue. Now note that after I cut these objects, then they're independent, these two pieces, and I can cut them again differently. So the second level, the first level cut was this. The second level cuts may not be next to each other. I mean, may not be continuous. I mean, one can be here, other can be here. It may not be like this. So I just want end-to-end on the smaller subpiece, not the entire piece. And it has connection with other packing problems. So, for example, bin packing, knapsack, strip packing, these are all studied under guillotine constraints. And for bin packing, there is a AP task. For 2D knapsack, there is a PP task. For 2D strip packing, there is also a PP task, and there is a tight absolute approximation guarantee. Okay. So this cutting sequence you can think of as a binary tree, where each node corresponds to some rectangular region, and each non-leaf node contains 2 children, which are obtained by this cut. So think of this previous pattern. So this was the initial object, and I cut like this. So I get 2 smaller subpieces. Then again, I cut like this. I get 2 smaller subpieces and continue. And at the end, the leaf contains only 1 rectangle in per piece. So then we call these leaf pieces are separable. I can cut out these leaf pieces. Now we call a rectangle is extracted if it is not killed or crossed by any of the cuts, and at the end it is the only rectangle in its subpiece. So in this example, when I have this cut, I kill this rectangle to R2 because it's passing through R2. I cannot really separate out R2. And then I have the sequence, maybe I cut like this and this and then this. And then if you see, all these rectangles are in one, are the only rectangle in its subpiece. So all rectangles except R2 are extracted by this guillotine cutting sequence. So given configuration is guillotine separable, if all rectangles can be extracted using some cutting sequence. So this example I said, it's only showing one particular cutting sequence. It's not showing that it is not possible to do for any cutting sequence, but one can prove formally there are instances like this for which you cannot separate out all rectangles using a sequence of guillotine cuts. So for example, if you have this 4 pinwheel kind of a structure, whatever way you cut end to end, it has to cross one of the rectangles. You cannot extract 4 rectangles. At most, you can extract 3 rectangles. So then the question is, can we separate out at least a constant fraction of rectangles? So if you have n rectangles, can we get, let's say, n to the power n by 10 or n by 15? And it seems, yeah, it should be. And there's a conjecture by Parker and Tardos, almost 22 years old, which they conjecture it to be true. And it remained a big open question in this area because it has connection with other problems as well. We'll see the connection of this problem with MISR as well. So what is known for now is in this kind of a instance where it's basically coming from the previous instance only, but it's more square-like objects. If you're given n rectangles, then in this instance, you can show that you cannot separate out more than n by 2 rectangles using a sequence of guillotine cuts. So there is a factor 2 loss that will happen. On the other hand, the best known algorithm or even existential result shows that you can always separate out n by log n plus 1. Actually, it's order log n, I can say. A slight improvement is there. Rectangles using a sequence of guillotine cuts. So there's a huge gap. I mean, the conjecture is it's a constant. In fact, 2 is the conjecture that you can always separate out n by 2 rectangles, but we have n by log n. So 2 and log n. There are this huge gap, but nothing is known. So let me, okay, how much time do I have? Maybe at 3-4 minutes. I'll just briefly tell you the proof of n log n plus 1, and then tomorrow we can resume. So one observation you have is if all rectangles intersect a straight line, then they are guillotine separable. So this red line, it's crossing all the rectangles, and then I can separate out all the rectangles by the second stage of guillotine cuts like this. You can also extend it to say that, okay, if all rectangles intersect a T like this, so T can be like this or even this, depending on the arms are 0 or not. So if they intersect all rectangles intersect some T, then they are also guillotine separable. And using this property, we can have log n plus 1. There is a question. Either aim to find the location of independent set of rectangles and then separate out. Then we can use trapezoidal map. Yeah, actually, the locations are easy to find. There are only 2n locations. I mean, I will show, but I mean, you have n rectangles. So independent sets, you can stretch things, and the only interesting regions which are interesting are basically the corner points. Other points are not so interesting, and there are only 4n square corner points. So it's not the location of independent rectangles, but exactly find out what are the rectangles. That is the problem. So location is fine. The DP will find all the possible locations and then find it out. But then the point is, what is the best independent set? That we don't know. Okay, so yeah, so we can assume the rectangles are embedded in some 2n cross 2n grid with integral corners, because I can always consider the endpoints of the rectangles, and there are n rectangles, 2n endpoints on each of the dimensions, and then just make this non-uniform grid to a uniform grid. So then what I'll do is I'll create. So do I have 2 more minutes, Arijita? Or okay. So then what I do is I create this log n number of levels. So what I start with is this 0, this is 2n. At level, I look at the this width n, and I create this red pole, and then I look at n by 2 and 3n by 2, and I create this green pole and continue. So there are total log of 2n or log n plus 1 levels, and that will decompose this plane. And what I'll define is for a rectangle, the smallest level which is intersecting the rectangle, I define it to be the pole. So in this case, red rectangles are the level 1 rectangles because it's intersecting this red line. Then the green one is level 2. So the red one is already intersecting level 1, so it is getting already level 1. So though it is intersecting level 2 as well, I will assign it to the smallest level. So this way, I can partition this n rectangles to log n number of color classes. And then I claim each of these color classes are guillotine separate. So think of some color class like gray. So what I can do is I can take all the previous levels, and let's say they are red and green levels. They are partitioning the rectangles into several regions. And then if I look at any of the inner regions, then these rectangles are intersecting a single line. So I already proved if all rectangles intersect single line, I can separate them using guillotine cuts. So each of these color classes can be separated by guillotine cut, and that is giving you a separation of n by log n plus 1. And what one can show, you can slightly improve it to something like log n plus 2 base 3 using the property of t cuts. Then the question was, can we improve this further if you use more complicated guillotine cuts? And we showed it's not true. But I mean, till now we talked about guillotine cuts and showed this result. Now, what turns out, there is a connection between these guillotine cut objects and MISR. And maybe today I don't have time to go over this. So we can show that whatever, if you show that given n non-overlapping rectangle, I can always separate out n by alpha fraction of the rectangles by guillotine cuts, then that will imply an alpha approximation for MISR. That is the connection. And yeah, I don't know. It will take 5 minutes to explain this, I guess. So maybe it's better to stop today, or yeah, maybe tomorrow we can continue from here.
Yeah, it's better we do it tomorrow.
Yeah.
Yeah. Thanks, Arindam, for the very nice talk. So, any questions?
So just to relate to the DP approach, the divide and conquer DP approach you talked about for the interval thing, right? So this cut, they were also kind of the guillotine cuts, right? I mean, so okay, so that's the intuition that you will.
So I mean, there you don't even need cuts; you need points basically. Points. Sure. Now you have guillotine cuts extension. Now we'll see that I mean, the conjecture is alpha equal to 2. So we should get a 2 approximation if we prove this conjecture.
Sure.
But the hardness is in the analysis. How do you prove this? So it seems that if we have the guillotine cuts, we don't have too much power. So what in the next lecture, what I'll show is you can have bends here. Instead of one guillotine cut, now you can have more and more bends. And the bends can avoid cutting more rectangles. And finally, we'll use that property to show this 2 plus epsilon approximation. So there are two questions. One is, do horizontal cuts are always vertical or horizontal lines, or bends possible? So yeah, by definition, guillotine cuts are end-to-end horizontal or vertical cut and they're axis parallel. But you can also have non-axis parallel cuts as well in guillotine cuts. But in axis parallel rectangles, actually those will not help. You can show that for axis parallel rectangles, whatever you can do with axis parallel guillotine cuts, you can do with arbitrary guillotine cuts as well. But bends also will do in the next part. Instead of cutting like one straight line, we can have some axis aligned set of line segments like this, which will have the cut. So like instead of this kind of a guillotine cut, we'll have bends, and that will help us later. And does it help if all the rectangles and squares are of the same dimension? So what do we mean by dimension? You are saying the ratios of width and height are similar?
So assume lengths are same.
Yeah, then
All
actually,
of them are of length 1.
all are of, yeah, I mean, actually both the cases can be solved. There are two cases. One is when, so for square case, actually, we have proved this conjecture. So for squares, we showed around 60 or something. I forgot the exact ratio, but some constant. This conjecture is true. So given embedding of n non-overlapping squares, you can always find n by, let's say, 81 fraction of squares, which are separable by guillotine cuts. For squares, it is true. But for rectangles also, if you have same dimensions, so if the ratio of width and height is similar for all rectangles, then what you can do is you can stretch things and make them square-like objects. So instead of square, I can say if the width by height ratio is constant, they're like fat objects. So they can also be handled by this approach. Or if all the rectangles have same width or same length or almost same width or same length, that also can be handled. Those are special cases which can be handled. But in general rectangles, you can have arbitrary ratios, which creates the problem.
Okay, any more questions? There's another question.
Okay, why cannot we use arbitrary square algorithm for arbitrary line segments to get figures? I guess we can translate a line segment in a square. So for arbitrary line segments, you mean even for axis parallel, let's say arbitrary is much more harder. You have any orientation, but even if you take, let's say, axis parallel line segments, then the square algorithm will not work. So what square algorithm you want to use? Let's say you want to use greedy algorithm. Or so if you remember, okay, can you tell me which square algorithm you want to use, like greedy or shifted grid or quad tree? Which one? Because each of these has different problems. So if you have, let's say, shifted grid or quad tree kind of algorithm, what it does is it divides. It's either divide and conquer policy, but then it creates some kind of smaller cells, and it uses the property that if you have squares, then in this smaller cells you can have only constant number of squares, and that you can solve in brute force way. But if you have arbitrary line segment, you can have arbitrary mini line segment within the cells, so it will not extend to that case. So there are several technical difficulties if you want to extend the square algorithm even to arbitrary line, even to axis parallel line segment, because it's not generalized. The square is not a generalization of axis parallel line segment. It's a different case.
A volumetric argument won't work. Yes. Volume argument won't work, to just say that.
Yeah, exactly. The volume argument will not work. So for fat objects, we know that it has large volume, and that helps in these smaller grid cells, which does not work here.
So okay then. So we end the session here. Thank you, Arindam,
Thanks a lot
for this wonderful talk. We will look forward to your next talk tomorrow. And thank you everyone for attending this. So I think I will give my. I think Shamantak, you have to take over now. Is it? Who's the next person?
That's correct. Yes.
Okay.
Unless.
So we meet in 2 minutes, something like that.
I think I will just set it up with them only. I think he's here.
Okay. Thank you. Thank you.
Thanks.
Thanks a lot.
Thanks, Arindam. So the organizers, is there anything you want to say? Otherwise, we can just set it up.
No, you can, I think, continue.
Okay. All right. So Demalada, can you try sharing your screen? Oh, I think he has to be made co-host. Yeah. Okay, now I'm the co-host, so I guess I can make you the co-host. Okay, I cannot make Devmale the co-host, so I guess Sushmita, you have to do it.
Just give me a moment.
Yeah.
Yeah, because of list of participants being long, it's taking a bit time to find the right, the name to make co-host. She's doing it. Just give a moment.
Sure, take your time.
I've done. Devmalo, I think you should be able to share now.
Did that work?
Yeah.
Okay. Can you hear me as well?
Yes, it's fine.
So, Shamantak, do you mind monitoring the chat?
Sure.
No,
And-
that's fine. So should I let you know once there is a question, or?
Yeah, absolutely. Like, feel free to stop me.
Right.
I mean, I'm fine with people raising their hand or stopping me, just starting to speak and stopping me forcibly. But
Yeah.
yeah.
Okay.
Monitor the chat in case there are questions there. Thanks.
Right. Yeah. So I'll keep an eye on the chat. So Sushmita, shall we start or just wait for maybe another minute?
I think we can start.
Okay. Yeah, it's like 11:16. So okay.
Yeah.
Okay. Yeah. Welcome to the second session of RTA 22, and thanks to the organizers once again for organizing this one. We have been missing this in the last year. So we are delighted to have Demalya Panigrahi for the second talk of today. So Demalya is an associate professor of computer science at Duke. So after receiving his PhD from MIT, he worked as a postdoc for a while at Microsoft Research Cambridge before joining his current positions. So Demalya's main interests lies in a variety of algorithmic problems, mainly on graphs, and also in the area of so-called algorithms under uncertainty, which I guess encompasses mostly online algorithms. But as far as I am aware, he also dabbles a lot into related areas like algorithmic game theories, approximation algorithm, and so on and so forth. So honestly, like I have been fascinated by his by his earlier papers on graph sparsification and so on and so forth. But more recently, he, along with some of his co-authors, they have some very exciting breakthroughs in the fundamental minimum cut problem in graphs. And not only is it a standalone result, but it has also opened up several new avenues to tackle problems in network flows, cuts, connectivities. And we hope to hear about some of these progresses from Demalya over the two talks that he's going to give. So Demalya, over to you.
Thank you, Shamantak. So as I was mentioning during the break, feel free to stop me if you have any questions. I'd be happy to take questions during the talk. Also, thanks to the organizers for inviting me. Thanks to Shamantak for this generous introduction. And thanks to everyone for showing up. I guess it's a slightly better time than it is out here, but still, thanks for showing up. So I'm going to be talking about minimum cut algorithms, and I have roughly split my talk into two parts. The first part will focus on this new technique called isolating cuts and some of the ramifications of this technique. The second part will go into some other things. The two parts may not be like completely balanced, so I might not finish the entire first part of the talk today, but we'll see how far I get. Okay, so this is based on joint work with a lot of people over several years and many papers. So I just wanted to mention everyone who has been involved in this process. So that's Amir Aboud from Weizmann, Roby Krautgamer, also from Weizmann, Ohad Trabelsi, who is a postdoc at Michigan, Ruoshu Chen, who is my student at Duke, Saura Chai, who is a PhD student at Aalto, Hachapal Saranurak, who is at Michigan, Kent Conrad from Purdue, Danupan Nanongkai, who is currently at Copenhagen but is moving to MPI soon, and Jason Lee. Last but not the least, I mean, he has been my closest collaborator in this line of work for several years now. So Jason is a postdoc at the Simons Institute, Berkeley. So let's start by defining a cut. This is something many of you already know. But a cut is simply a set of edges whose removal disconnects a graph. Okay, so it splits the graph into multiple components. And the minimum cut is a cut of minimum cardinality, so it's a minimum count of edges, or minimum weight if the edges have weight. And sometimes when we take the minimum, we focus only on cuts satisfying some particular condition. So sometimes we would be talking of minimum cuts that are sort of unconditionally the minimum. Sometimes we'd be talking about minimum cuts that are minimum among some subset of cuts. From the context, it would be clear which minimum cut we are talking about. In this talk, all graphs are going to be undirected, except on the last slide when I'm going to talk a little about directed graphs. The graphs can have parallel edges, so you can have multiple edges between the same pair of vertices. And the edges can have non-negative weights for the most part. Okay, so the first two types of graphs here are allowed. The first graph has non-negative weights. The second one has parallel edges, but the third one is not. So you cannot have directions on the edges as far as this talk is concerned. Okay, so the first type of minimum cut that we are going to be talking about is what's often called a global min cut. So this is simply a minimum cardinality or weight cut of the graph. So there's no conditions. Look at all the cuts of the graph, whichever has the fewest edges or has the minimum edge weight. That's what a global min cut is. We'll also be talking about ST min cuts, sometimes also called local min cuts. So this is again a minimum cardinality or weight cut, but with one condition. So there are two specific vertices, S and T, and these two vertices should be on different sides of the cut. Okay, and we know the famous max flow min cut theorem, which states that ST max flow is equal to ST min cut. If you haven't encountered max flows, that's fine. We are not going to be actually talking about any flows today, but I'll mention the word max flow, and whenever I do so, you should map it to ST min cuts. Okay, so an ST min cut can be obtained by running any max flow algorithm. This is a basic fact that we are going to be using throughout the talk. Okay, so here's an example of a graph. So in this graph, if I wanted to figure out what the ST1 min cut is, then as you can see, the smallest cut that separates S and T1, that has S and T1 on different sides, is the cut in the middle. So the cut containing that single edge of weight 1. That cut also happens to be the global min cut in this particular graph. But if you wanted the minimum cut that separates S and T2, so that's an ST2 min cut, then the global min cut has both S and T2 on the same side of the cut. So that's not a candidate anymore. So in this particular graph, the minimum ST2 cut is the cut containing the 2 edges incident on S. Okay, so that's a cut of weight 2, whereas the global min cut was a weight 1. All right, so these are the basically the 2 min cuts that we are going to be talking about today. And here's a very simple global min cut algorithm. Maybe the first algorithm you would think about if I asked you to find an algorithm for global min cuts. So fix an arbitrary vertex in the graph. Let's call that S. Now what you do is you find ST min cuts for all other vertices T. So you iterate over all the other vertices of the graph. There are n-1 vertices. So throughout, I'll use n to denote the total number of vertices, m to denote the total number of edges. So if n is the total number of vertices, then there are n-1 vertices other than s. I iterate over all these vertices. For each such vertex, I denote it t. And then I find the ST min cut running max flow. And then eventually, after I'm done with all the n-1 iterations, I report the smallest of these ST min cuts as the global min cut. Why is this a correct algorithm? Well, the fact is that once I have fixed the vertex S, there must be at least one vertex that's on the other side of S, that's on a different side of S from in the global min cut. So there's at least one vertex that's separated from S in the global min cut. I don't know which vertex it is, but if I iterate over all the vertices, I'll hit that vertex at some point, and therefore at that point I'll get the global min cut as my ST min cut. Okay, so it's a correct algorithm, and therefore the global min cut problem actually reduces to just n-1 max flow calls. So that's the baseline algorithm, but that's not where the state of the art is. So if you look at what has happened over the years, here's a very brief summary. There's a very large amount of literature on the problem. It's one of the basic questions in combinatorial optimization. But in short, the top box contains this naive algorithm of n-1 max flows. And I've actually quoted the running times for this algorithm, assuming you use the best max flow algorithms that we have available today. It's not very important to note what those times are. It's kind of complicated. We'll get back to those later. But there are better algorithms for global min cut, better than this naive algorithm. In particular, in the early 90s, there were a spate of algorithms, all of which got the same running time. The running time was m times n. And I'll use this O tilde notation to hide subpolynomial factors, so things like polylogs and so on. There are many polylogs in all these runtimes. We are not going to be talking about those. So you can get a running time of m times n deterministically using any one of these algorithms that came in the early 90s. And then there were a series of randomized algorithms. So the first one perhaps is the Karger-Stein algorithm, also called the recursive contraction algorithm. So this obtained a running time of n squared. So remember, for a connected graph, n squared is better than m times n. And then that was further improved to a running time that's nearly linear. So it's almost m by Karger in 1996. And this is really the best you can do, modulo those polylog factors that I'm hiding. Because even to read the input, for if you wanted to read in a graph, you would spend at least m time because there are m edges. So you have to read in, for example, m weights. Now, one interesting thing to note is that if you compare the running time with a single max flow call, then the deterministic runtime for global connectivity, for global min cut, is actually slower than max flows. So we can deterministically find max flows much faster than m times n. On the other hand, the randomized algorithm is a linear time algorithm, so that's much faster than max flows. We still kind of don't know how to do max flows in linear time. Okay, although I'll qualify that statement a little later. Okay, so that's the state of the art, and it has this like strange situation where if you were willing to use randomization, then you can then the global min cut problem seems to be easier than ST min cut. if you wanted to be deterministic, then the global min-cut problem seems to be slower, seems to be more difficult than ST min-cut. So when we set out in this project, maybe the first question that intrigued us was the following. So we were just wanting to find a deterministic global min-cut algorithm that could match a deterministic max flow algorithm. Okay, because as I said, there was this strange inconsistency that if you wanted deterministic algorithms, global min-cuts had slower runtimes than max flow. Again, this question, at least one form of this question, was asked originally by Karger in the mid-90s. There was no progress on this for almost 20 years until this beautiful paper of Kawarabayashi and Tharup about 6-7 years back. So they showed that, in fact, you can solve global min-cut deterministically in near linear time, in O tilde m time, which is the same as what you can do randomized, but with the crucial restriction that this algorithm only works for simple graphs. Okay, and this restriction is kind of pretty, this is a significant restriction in the sense that it's not just that the algorithm is slow if your graph is non-simple, but the algorithm is actually wrong. So it doesn't give you the correct answer if the graph is non-simple. And I should mention that this paper actually won the Fulkerson Prize last year. Okay, so we had this for simple graphs, but we didn't know what we could do if there were parallel edges. We certainly didn't know what we could do if edges had weights. There was an improvement by Monica Hensinger, Satish Rao, and T. Wang. But the improvement is only in the polylog factors. So the original result had something like log to the 12. I think after the improvement, it went down to log squared. And the improvement was also important in terms of providing a new combinatorial perspective to the algorithm. But fundamentally, it didn't change the state of the art in the sense that we still didn't know what to do if we wanted to go beyond simple graphs. So our main theorem, the first one in this line of work, this was work with Jason Lee, was that there is a deterministic algorithm for the global min-cut problem that runs in time that's equal to polylog max flow calls. Okay, so this is not quite as good as you might hope. So this is not quite getting it down to near linear time, which you can do if you were allowed randomization, but this is getting close. It's at least getting it down to max flow. Okay, and in fact, Jason didn't quite stop there. So in a follow-up work next year, he actually showed that you can go all the way down to near linear deterministically. So I won't actually talk about the second result because that will be a detour. It uses a set of techniques that are different from what I want to talk about. But I'm going to talk about my result with Jason because that will introduce this very nice idea of isolating cuts that we are going to see quite a lot of. All right, so as our main new idea in this result is isolating cuts. So what are these? So let's go back to the simple min-cut algorithm that we started with. So recall this algorithm. What did it do? You fixed an arbitrary vertex as S. Then you found ST min-cuts for all the other vertices designated as T. And then you reported the smallest of these ST min-cuts as your global min-cut. Now let's do a thought experiment. So suppose after you had fixed this vertex S, someone came and gave you some vertex T that's on the opposite side of S in the min-cut. Okay, so this is some oracle that gives you a vertex T. Now, if you got hold of such a vertex, the vertex T that's on a different side from S in the min-cut, then all you would do is you would just find the ST min-cut for this one vertex T, and you would report it as the global min-cut, right? So in some sense, the previous simple algorithm, what it's doing is it's kind of blindly searching for a vertex T that's on a different side from S. Okay, and that kind of raises this natural question, is there a way to efficiently do the searching? Can we find vertices S and T that are on different sides of the global min cut in some efficient manner? If we are able to do that, then once I have these two vertices, I can just run max flow and I will be done. Okay. So now let's look at this question in two different cases. The first situation is if when the min cut is balanced. By balanced, I mean that you have n over 2 vertices on each side of the cut. So that's perfect balance. Don't quite need perfect balance for a statement of this sort, but let's go with that. So if your min cut is perfectly balanced, you have exactly n over 2 vertices on both sides. Then finding a pair of vertices S and T that straddle the min cut, that are on different sides of the min cut, is kind of simple. So all you need to do is just sample two vertices uniformly at random. And with about probability half, you will have these two vertices on different sides of the min cut, right? So with a probability about a half, both of the vertices would be on the same side. With probability about a half, they would be on different sides because your two sides are balanced, okay? So with probability half, you have a good pair of vertices, a pair of vertices on which you can run max flow to find your min cut. And if you wanted to boost this probability further beyond half, all you do is just repeat this process a bunch of times. Okay, so you sample log n times instead of just once. So then the above property holds with high probability. So there's at least one pair ST that's straddling the min cut. And then you just return the smallest ST min cut across all these log n runs. Okay, so if the min cut is balanced, then in fact you have a very simple algorithm. Of course, I'm using randomization here, and my whole purpose was not to use randomization. So we'll go back and fix that later. But for now, let's allow randomization. Let's try to develop our ideas a little better. So if the min cut is balanced, we have a simple solution. The problem is if the min cut is not balanced. So let's say the min cut has only k vertices on the smaller side, and think of k as being small. Then one thing I could do is I could sample vertices at rate about 1 over k. So I just take each vertex independently, sample it with probability 1 over k. If I do that, then with constant probability, I'll have exactly one vertex on the small side in the sample, right? Because I'm sampling k vertices, what's the chance I'll sample exactly one of them? If I'm sampling at rate 1 over k, that's a constant, right? Because I expect to see one vertex. And I'll have a constant probability of seeing exactly one. Now I can repeat this process log n times. I can sample log n times. And again, this property that you see exactly one vertex on the smaller side in one of the samples, this property now holds with high probability. Okay, but this should raise sort of two red flags. The first one is we don't quite know k. So remember, k is the number of vertices on the smaller side of a min cut. So we don't quite know k, so we don't know what rate to sample at. But this turns out to be a fairly trivial problem, minor problem that we can handle. We'll see how to handle it later. The much bigger problem is, let's say k equals 1. So I have exactly one vertex on the smaller side. Then what I'm saying above is that I sample at rate 1. So with probability 1, I'm sampling vertices. What does that mean? I'm basically taking all my vertices. So really, I have hit the smaller side at exactly one vertex, but I haven't really reduced the number of vertices in the graph. So if I haven't reduced the number of vertices, how am I hoping to get any benefit out of that process? Okay, so remember in the previous algorithm, we were sampling two vertices, S and T, in the balanced case. So the fact that we had just two vertices allowed us to run max flow. If you have a bunch of vertices in my sample, how do I run max flow, right? And of course, if I have n vertices, which would be the case if k equals 1, then I certainly can't run max flow for all pairs. That's way too expensive.
So I'm just trying to understand. So for k equals to 1, the problem is anyway easy, right? You can just check the degree. Okay.
That's
okay. Yeah.
That's right. Yeah. So this is just for
illustration.
Yeah. For illustration of the fact that by itself, the previous property is not useful. As Shamantak says, if you knew k equals 1, you could just check degrees. But instead of k equals 1, think of k equals 100, for instance, let's say. Okay.
Hey, but like when k is rather a quick question, but k is small, like other arbitrary, like instead of picking a pair, you could have fixed an S and then tried to find a T.
Right. So finding the T is where the problem lies. So let's say k equals 100.
Right.
So if you actually wanted to find a T in that set of 100 vertices, you end up sampling at least like something like n over 100 vertices. Right. So you have just reduced from sampling n vertices to sampling n over 100 vertices. That's not going to give you any improvement.
I guess what I'm trying to get at is like if it's imbalanced, then like picking an S with like say it's some constant probability tells me that it's on the larger size.
That's right.
But then I can say probably just find min cuts to all other vertices from S. But you're probably saying that that's a expensive process.
Well, that was the original simple algorithm, right? That's going to take n minus 1 flows.
Okay.
Does that make sense?
It does. It does. Yeah. Thanks.
Yeah. Any other questions before I keep going? Okay. Right. So let's keep going. So let's look a little deeper into what's really going on. So let me denote the smaller side of the min cut by S. And as we saw in the previous slide, if we are able to sample at rate 1 over k, where k is the size of S, then let's say we can obtain a sample of vertices that we call T that has this property that there's exactly one vertex in which it intersects with the smaller side. Okay, so this is something we can obtain. The thing that we can't control is the size of T. So as this previous discussion told us, T can be as large as n over 100, for instance. Okay, so let us define a new problem. So let's suppose we are given a graph and a subset of vertices T. Now, we define a problem which asks us to find a set of cuts, not just one cut. It asks us to find the following cuts. For every vertex in T, I want a minimum cut that separates this vertex little t from the rest of the vertices in capital T. Okay, so one way of thinking of this is that you fix this vertex little t, contract all the vertices other than little t into a single super vertex, let's call that S, and now find the ST min cut. Okay, and I want you to do this for every single vertex T in the sample capital T. Okay, so if you could solve this problem, then you would be done, right? Because you know that at least one of these vertices in capital T is the unique vertex on the smaller side of the min cut. I don't know which that vertex it is, but there is one. So at some point, I will hit that vertex as little t. Okay. All the other vertices in capital T are on the larger side of the min cut. So now if I ask for the minimum cut that separates little t from every other vertex in capital T, then that minimum cut will be the global min cut. Okay, simply because the global min cut has exactly this one vertex little t on the smaller side in the set capital T. Okay, so this is what we call the isolating cuts problem.
Malak, could you repeat this? I couldn't follow very properly. So could you repeat this?
Okay. Okay. So suppose I give you a graph and a subset of vertices in that graph. And I also tell you that there's some vertex hiding in this subset. That's a unique vertex on the smaller side of the min cut. Okay. So every other vertex in capital T is on the larger side. There's one unique vertex in capital T that's on the smaller side. You don't know which vertex it is, but there is such a vertex in capital T. Okay. So now if that vertex, if I call it little t, then the minimum cut that separates little t from all the other vertices in capital T is in fact the global min cut as well.
Correct.
Okay. So now if I can find all the minimum cuts that separate all the candidates little t from the rest of the vertices in capital T, then among them, whichever is the smallest will be my global min cut.
Okay.
Does that make sense?
Yes, thanks.
Right. Any other questions? Okay, so that's what we are going to call the isolating cuts problem. Okay, so I'll give you a graph, I'll give you a subset of vertices. Can you find me the isolating cuts? Where what are the isolating cuts? These are the cuts that isolate a single vertex in this subset from the rest of the vertices in the subset. Okay, it's the minimum cut that isolates a single vertex in the subset. So again, important thing to note, it's not one cut. So when I give you the set T, the number of cuts I'm asking for is the size of T. For every vertex in capital T, I'm asking for a minimum cut. Okay. So how do I solve isolating cuts? So of course, the naive algorithm would be to iterate over all possible values of little t. So I take every possible vertex in capital T, contract the rest of the vertices into a super vertex, find the ST min cut. The problem, of course, is that this takes something like T max flow calls. Actually, it shouldn't be T minus 1. It's actually T max flow calls. But T itself, the size of this subset that I give you can be as large as n. I haven't actually I haven't given you any guarantees that the size of T is small. Okay. So, and in particular, in that case that we saw earlier, where k equals 1, the size of the sample will in fact be n. Okay. So this naive algorithm is no good because this is really taking us back to this algorithm that's running in max flows. Our main contribution in this paper is what we call the isolating cuts lemma. So we show that the isolating cuts problem can be solved in log T max flow calls rather than T. And this is interesting in the sense that the number of cuts that I am retrieving from this algorithm is actually a lot more than the running time of the algorithm. Remember that the number of cuts that I am retrieving is like T. On the other hand, the number of max flow calls that I am making is only log T, right? So which is kind of seems a little strange, right? Because that says that somehow I'm managing to retrieve a lot of cuts from a single max flow call, right? And we'll see how that happens. Any questions about the statement? The next few slides will aim to prove this statement, at least to some extent. But
could you repeat the last statement?
Could I repeat what? Sorry.
The last statement.
Yeah. So the isolating cuts lemma says that this isolating cuts problem. So the isolating cuts problem is the stuff in black on top. This can be solved using log T max flow calls rather than T max flow calls, which would be the naive way to solve it. Okay.
Hey, Demalia?
Yeah.
So do you really need the size of key min cuts, or do you just want the min over all such cuts?
I just need the min over all such cuts, but I don't know of a way to do that better than actually finding all of them.
Yeah, okay, thanks.
Okay, all right. So let's delve into isolating cuts a little more. Okay, so here's, I'll actually give an algorithm for this. So for the isolating cuts problem. So let's say I have this graph that I have shown here, and the vertices I have circled in green are the vertices in T. Okay, so the vertices T0, T1, T2, and T3 are the vertices in capital T. Now, the first thing I do is I encode these vertices in binary. Okay, this encoding is not so important how precisely it's done, but for the sake of concreteness, let me encode it as 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now what I do is I look at every individual bit position. So let's say I'm looking at the first bit position, the most significant bit, and I partition the vertices in T into those that got an encoding of 0 and those that got an encoding of 1. Okay, in this particular example, if I'm doing the partitioning based on the first bit position, then A and C are on one side of that partition, B and D are on the other side of the partition. Now what I do is I contract all the vertices that got a bit position, a bit value of 0, contract all the vertices that got a bit value of 1. Okay, so this creates a pair of super vertices, and I just find the ST min cut for this pair of super vertices. Okay, so for bit position 1, I'll find the minimum cut that separates AC on one side and BD on the other side. The minimum cut in the graph that under this constraint, under the constraint that AC is on one side and BD is on the other side. And I'll do this for every bit position. So when I get to the second bit position, now AB is on one side and CD is on the other side. Okay, so I find these, I run these max flows and I find ST min cuts for each bit position. Okay, so of course these are log T, the number of like I'm encoding T bits, T vertices. So the number of bit positions is log T or O of log T. And therefore these max flow calls are returning O of log T cuts. But the important thing to note is that every pair of vertices in T, these got different bit encodings, right? If I take any pair of vertices, they have different bit encodings. What that means is that at least one of these log T bit positions, the encoding differs, right? So one vertex got a 0, the other vertex got a 1, at least at one bit position. Okay, so every pair of vertices in T is separated by at least one of these log T cuts. So what this means is that if I take all these log T cuts and remove all those edges from my graph, then in fact I will split the graph up into at least T pieces. And in each of these T pieces, I'll see exactly one vertex from capital T. Right? So again, why is that the case? For any pair of vertices, they differ in some bit position. So when I remove the min cut for that particular bit position, that pair of vertices will get separated. They are no longer connected. Right? And this will happen for every pair, which means that when I remove all these log T cuts from my graph, I'll split the graph up into pieces, at least T pieces, and I'll see only one vertex from T in each of these pieces. Okay, so that's a basic observation that's going to be important. So now what I do is I take these pieces individually. So in this particular picture, I call these pieces S0, S1, S2, and S3. So as you can see, T0, T1, T2, and T3 have gotten split into these 4 pieces. Now I take each of these pieces individually. For instance, let me illustrate it through S3. So I take S3, I take all the other pieces, S0, S1, and S2 in this case, contract everything else into a single super vertex. Okay, so this is phase 2 of the algorithm going on. Phase 1 was this bit position based partitioning. Phase 2, I take each of these individual SIs, contract everything else into a single vertex. Let me call that as ZI. Okay, so in this particular example that I have shown here, I have S3, which is uncontracted. Everything else, S1, S2, and S0, I contract into Z3. Okay. And then now note
do
that
S3,
yeah.
Sorry, do S3 will contain more than one terminal, one vertex from T?
Yeah, it cannot contain more than one. None of these pieces can contain more than one. So as we were just saying, if you have take any 2 vertices from T, one of the bit positions in one of the bit positions they differ. So that particular min cut will separate the pair.
Okay, thanks.
Okay. So S3 contains some unique terminal. Let's call that T3, some unique vertex from T. Now what I do is I find a minimum cut from T3 between T3 and this contracted vertex Z3. Okay. So for a second, let's step back. What were we really intending to find? We were intending to find the minimum cut between T3 and the terminals T0, T1, and T2 contracted. Okay. Now, in general, in this particular example, S0, S1, and S2 are exactly the terminals, but in general, they can contain other vertices. So what I'm ending up finding is not T3 contracted and T0, T1, and T2 contracted on the other side. But what I'm ending up finding is the minimum cut with T3 on one side and all of S0, S1, and S2 contracted on the other side. Okay, so a priori, it's not clear that I'm finding the right set of cuts. Okay, but at least there's some semblance of going in the right direction, right? Because I was interested in finding these cuts that separate TI and all the other terminals. Instead, I'm finding these cuts that are separated by TI and all the other terminals, but plus other things. Okay. Was there another question? No. Okay.
So far you were like invoking max flow only on the original graph, but now you are invoking it on this induced graph GI.
That's right. That's
and
right.
the hope is that in an amortized sense, the size of GI would be small.
Perfect. Yeah, we are getting there.
Okay.
I have a question. So these S0, S1, S2 contains vertices apart from the terminals as well, right? So
they can, yes.
Okay.
Yes, yes. In general, they can. In this particular example, it doesn't, but in general, they can, yes.
Okay, thank you.
Any other questions? Okay. So this is really the picture I have. So I have this sort of giant vertex Zi containing everything else, all the other SJs. And I have this uncontracted part Si containing this terminal Ti, containing this vertex Ti from T. Okay, so the first claim is that in fact the Ti Zi min cut in this graph GI, which is this contracted graph, is in fact a min cut, also a min cut between Ti and the other terminals. Okay, so this is not obvious, but the proof is not so difficult. It's by some standard property of min cuts called uncrossing. That's something I'm not going to talk about. Like, I'm not going to describe this property here because it'll be a bit of a detour. But this is uses fairly standard techniques. Nothing special going on here. Okay, so I am finding the right cuts. Now, how many max flow calls is my algorithm making? So there were two phases, remember. The first phase was this phase that used these bit positions. So there, clearly, we are running log T max flow calls because there were only log T by bit positions. So that's great. Problem is the second phase. The second phase is actually using T max flow calls because there are T different SIs, and for each of them, I'm running max flow. But now if you look at the actual graph on which I'm running max flow, then you notice that there are two types of edges. There are edges that are inside any of these sets Si. So these edges only appear in one of the calls, right? Whichever, if an edge is inside a segment Si, then it only appears in the ith call. It doesn't appear in any other call. But there are also edges that cross between segments. So let's say there's an edge between Si and Sj. Now that edge can appear in at most two calls. So it can appear in the call for Si, the max flow call for Si. It can also appear in the max flow call for Sj, but not more than that, only two. So that says that cumulatively across all these T max flow calls, we are operating only on 2M edges or O of M edges. Okay, so that's where this inconsistency is being resolved. So remember, I told you that we are finding T cuts, but we seem to be only using log T max flows to find these T cuts. So really what's going on under the hood is that we are running T max flows. It's not log T max flows, but the way we have set it up, we are ensuring that cumulatively these T max flows are only operating on 2 times M edges. So really the dominant term is the first round that's actually running log T max flows on the original graph. The second round, which is actually running T max flows, is only costs us equal to 2 max flows, something like that. Okay. So overall, when you put this together, then you have the isolating cuts lemma. So now we have found all the isolating cuts, and we have only used up log T max flow calls. Okay, so I'll pause for a second and take any questions. So we will now get into how to use the isolating cuts lemma. So firstly, if you miss something in the proof, you can rejoin now because we are not going to use that proof anymore. But if you had any questions about the proof, I can also answer them before we move on. Okay, so if there are no questions, let's now try to use this lemma. Okay, and let me start off by using it to define a simple randomized algorithm for min-cut. So as we said earlier, randomized algorithms are not going to improve the state of the art. We already have near linear time algorithms, but this will illustrate how the isolating cuts lemma can be used, and this will be useful later as well. So here's a very simple randomized algorithm. So what I do is I first try to guess the size of the smaller side of the min-cut. Okay, so remember we had that red flag earlier that we didn't know how large the smaller side is, so we didn't know what rate to sample at. But let's just try to guess this. So we try all possible values of the smaller side. I just scale everything by factors of 2 so that we don't have too many rounds of guessing. Okay, so I guess the value of I from 1 through log n, and the size of the smaller side is 2 to the I. Okay, for one of these i's up to a factor of 2. Then once I've fixed a value of I repeat the whole process log n times. This is just to boost the probability of success. Remember, we had this thing that the probability of success was only a constant. We need to boost this up to high probability. So we just repeat it log n times. But now I have fixed I, and we are in a particular iteration. Now what I do is I simply sample vertices at rate 1 over 2 to the I. I form a subset T and run isolating cuts. Okay, so now I have these log squared n rounds of isolating cuts. They return a bunch of cuts to me. Whichever is the smallest cut that I see, that's the one I output as my global min cut. Okay, that's as simple as the algorithm is. Why is it correct? Well, with high probability, there's an iteration where the smaller side of the min cut has exactly one vertex in T. This is an argument we have gone over earlier. The fact that we are sort of that our guess is missing the right value by a factor of 2 doesn't really make any difference. That just changes the constant. So there's an iteration where we are actually hitting the smaller side at one vertex. And in that iteration, the isolating cuts lemma will return the min cut. Okay. Now, of course, every cut that I return in the entire algorithm is a real cut of the graph. So at the end, if I'm returning the minimum among all the cuts I saw in isolating cuts, then that must be the global min cut as long as isolating cuts at some point gave me the global min cut. Okay. So that just establishes that the algorithm is correct. And of course, the running time is dominated by these calls to the isolating cuts lemma. So that's just polylog and max flows. There's really nothing else going on in the algorithm. Everything else is very efficient. It's just sampling. Okay, so that's a very simple randomized algorithm. But how do we de-randomize this? So if you go back to the randomized algorithm, the isolating cuts lemma itself was running a deterministic algorithm, right? So we discussed this algorithm, there was no randomization in it. The only randomization is in the sampling, in trying to obtain this set of vertices that hits the smaller side at a single vertex. Okay, so we need to de-randomize that. So let's call a set of vertices with this property that it hits the smaller side of my min cut at a single vertex. Let's call that an isolator. Okay, and our goal then is to find an isolator deterministically. If you're able to do that, then we can use the isolating cuts lemma. We would be done.
Hey, can I ask a quick question before you move on?
Yeah, absolutely.
So in the previous slide, for it's sort of stark that different T's. So let's say capital T and capital T prime, they don't help each other in the sense that if they're disjoint, then say supersets of each other, like one solution for one does not help. So you have to really do it for scratch for all T, or am I like maybe there's a smarter encoding that lets you.
It could be, but it would only save on logs, so we didn't really think about it.
Okay.
I mean, in any case, the total number of T's you're working with is like log squared.
Okay.
Okay. So, so our goal is to find an isolator deterministically. Was there another question?
Yeah, Demalya, so I just want to ask, do you want the size of the isolator to be the size of the smallest set of vertices, or does that not matter?
No, the size of the isolator will actually be roughly equal to 1 over T2 to the I times n.
Okay.
Right, where like you are at level I, and I have no idea what the smaller side looks like.
Right. Okay.
Okay. So how do I find an isolator deterministically? That's our new question. So first, let's extend the idea of isolators a little. And let's call a set of vertices an almost isolator if instead of hitting the smaller side at one vertex, it hits the smaller side at most a polylog n vertices. So this is saying that, well, I don't have too many vertices from the smaller side, but it's not, maybe not precisely one. It might be a little larger. It might be polylog n. Okay. And the translation from an almost isolator to an isolator is given by this claim. So we show that if you are given an almost isolator, then deterministically you can find a small list of subsets of this almost isolator such that one of these subsets is indeed an isolator, an actual isolator. Okay, and this uses something called color coding, which was introduced by Alon Euster and Zwick in a very different context. I won't go into this because roughly speaking, but as an exercise, what you can think about is the following. Roughly speaking, if I gave you an almost isolator, there is a very simple way of getting an isolator by just sampling the almost isolator. Okay, so and I'll if you are interested, I'll let you figure out how to do that sampling, but it's a very simple sampling technique. Really what this color coding does is it de-randomizes sampling. Okay, so this is just a clever way of doing the sampling deterministically. But from now on, I'm going to assume that once I have an almost isolator, once I have polylog n vertices on the smaller side, I'm done. I can rely on this claim from that point onward. Okay, so how far have we progressed so far? So we have said that given a subset of vertices whose intersection with the smaller side of the min cut is polylog n, given such a subset, we can find the min cut in polylog n max flow calls. Okay, so it's really a question of how to find such an almost isolator. So the technique that we use to find an almost isolator, we call that deterministic sparsification. Doesn't really have anything to do with like cut sparsification, which is a common topic in graph algorithms, but we couldn't find a better name, so we just called it deterministic sparsification. So what does this really do? So it says that suppose I give you some set of vertices T that's not an almost isolator. What does that mean? That means that T has more than polylog n vertices on the smaller side of the min cut. Okay. But importantly, assume that T actually does straddle the two sides of the min cut. So it's not all on the larger side. There are vertices from the smaller side, there are just too many. So if that happens, then the deterministic sparsification algorithm that we design, it computes a set of vertices T prime that has two properties. First, T prime reduces the size of T by a factor of 2. So T prime is no larger than half times T. And second, T prime continues to have vertices from both sides of the min cut. Okay, so you still have vertices from both sides. The size of the set drops by a factor of 2. Now note that it doesn't explicitly say anything about how many vertices it has from the smaller side. It's not that T prime is better in terms of directly getting you closer to an almost isolator. It's possible that T prime has just as many vertices on the smaller side as T did. Okay, so that's not our measure of progress, but T prime overall is becoming smaller. So if I have a deterministic sparsification algorithm, an efficient one, then here's our overall algorithm. So first we initialize T to be all the vertices V. Okay, so clearly at this point T does straddle both sides of the min cut trivially. Now we repeat multiple times, and we repeat until the size of T becomes really small, becomes less than polylog n. In each step, I don't quite know if T is an almost isolator or not. Okay, so let me assume that it's an almost isolator, and let me use color coding and the isolation cut lemma to obtain minimum cut candidates. This is assuming that it's an almost isolator. Of course, if it's not an almost isolator, I'm just getting junk cuts. Okay, so the first step is assuming that it's an almost isolator. Second step says, let me also assume that it's not an almost isolator, because I don't know what it is, like whether it is or not. So if it's not an almost isolator, then I have deterministic sparsification. So I also take T and I apply deterministic sparsification, and that halves the size of T. Okay, so what's really going on? I started off with all vertices. I don't know if that's an almost isolator. At that point, I assumed it is, ran my color coding and isolation cut lemma. I also assumed it's not, and I halved the size, and I repeated. Right, so at some point, either T becomes an almost isolator, because, right, or it continues to be not an almost isolator and therefore have more than polylog n vertices on the smaller side. So of course, if it became an almost isolator at some point, then that particular iteration, in that particular iteration, step 1 will actually find min cut. If it did not become an almost isolator at any point, now note that T has dropped to less than polylog n vertices at the end of this loop, right? So at this point, if it never became an almost isolator, then it must be that T is still straddling both sides of the min cut by the deterministic sparsification property. It's straddling both sides and it has only polylog n vertices. So at this point, by definition, it must be an almost isolator. Okay, so what we have established is that either T is an almost isolator in one of these loop iterations, or it's an almost isolator once I exit the loop. Okay, so now what I do is, after I exit the loop, I take all pairs of vertices in T, so there are only polylog n pairs, and I find max flow and add the ST min cut to my candidate. So if T is an almost isolator at the end, if it's still straddling the two sides of the min cut, then this last step will catch the min cut. Okay, so now I have created this enormous list of candidates. Well, I'm saying enormous, but polylog n list of candidates across all these steps. I look at all these cuts, and whichever is the smallest, I return that. Okay, so that's my entire algorithm. So as long as I have deterministic sparsification, I'm done. I have an algorithm that finds my min cut deterministically. All right, so I think I have a few minutes left. So I'll just finish deterministic sparsification and we'll take the rest of it tomorrow. Okay, so the missing piece is deterministic sparsification. And as I said, the goal is that if T is intersecting the smaller side at more than polylog n vertices, Then I want to halve the size of t, and I want to make sure that I'm still straddling both sides of my min cut. Now, intuitively, what we do is the following. So we want to find a vertex partitioning of the entire graph that has two properties. The first property is that it should have a small number of components in the partition. So I don't want to partition it into singleton vertices. Should be a small number of components. And I want to also ensure that the min cut does not cut into any one of these components. Okay, so let's say the min cut actually keeps all the components intact. The entire component goes to one of the two sides. If I suppose I had these two properties, then all I need to do to obtain t prime is just select one vertex in t from each of the components, right? Because the number of components is small, so that ensures t prime is small. Since the min cut doesn't cut through any of the components, by choosing just one vertex from each component, I ensure that my new set actually straddles the min cut as well. Okay, because all the vertices in a single component are on the same side of the cut. So by choosing any one and discarding the rest, I am not going to miss out on hitting any one side of the min cut. So if I had this kind of a vertex partitioning, then I'm golden. I can just choose one vertex from each of these components and I would be done. So how do I ensure these two properties? Remember, the two properties are small number of components, and the second is that I want my min cut not to be cutting into any of the components. So for small number of components, precisely what we want is the total weight of crossing edges. So the edges that go between the components, we want this total weight to be lambda, which is the size of the min cut, times the number of components t, times some parameter phi. Think of phi to be about 1 over polylog n. Okay, and if that is the case, then it's not hard to show that the number of components will be like phi times the size of t. Okay, so roughly speaking, now you can see the number of components is about t times 1 over polylog n times some polylog coming from the O tilde. So if I can adjust these terms, adjust the value of phi correctly, then I'll get like t over 2 components, or maybe t over 4 components. Now the other property was that the min cut does not cut into any component. For that, what we want is that every component expands. So if you're familiar with expanders, expanders are these graphs which where sort of if you run a BFS, then the BFS is very broad. Okay, it's a sort of a fat wide tree. So if you have an expander, then the min cut can't really cut into an expander too much, because if it cuts into an expander, then it will consume a lot of edges, right? So the min cut will not remain a won't remain a small cut. Right, so we want each component to be expanding, and we want the number of edges connecting the components to be small. Okay, and that there is a perfect tool for this that's called expander decompositions. So in particular, we use a deterministic expander decomposition, originally due to Chujoy et al., but the particular version that's most useful for us is due to Lee and Saranurag. Okay, so eventually what we have after, yeah.
So this is linear time, right?
This is near linear. So, right, so the Chujoy result is like m to the 1 plus epsilon time, where the epsilon goes into the value of phi. But the next one, Lee Saranurag, is actually near linear time. So that's like m times polylog. Yeah. Okay, so now I have my expanded decomposition, and really I have sort of 3 cases. I have trivial components where the component doesn't even intersect my set T. I have small components where the intersection is small. It's kind of like less than 1 over phi squared. And I have large components where the intersection is large. Okay. So now how do I select T prime? Trivial components I just ignored. It doesn't even have any vertex from T, so I don't care. The small components, I select any one vertex. Okay, the point is that there are very few vertices from T in these components. So even if I choose one vertex, I'm going to be so the min cut cannot actually cut in and isolate that vertex. The large components have a lot of vertices. I need to be a little more careful here. So here I choose about 1 over phi vertices. Okay, but remember the large components, each of them consumes 1 over phi squared vertices from T. So overall, the total number of vertices I end up choosing is something like phi times T. Okay, and this is exactly what was at most T over 2. Okay, so this slide, I'm sort of suppressing a lot of details. So if this seemed to sort of too hand wavy, that's fine. I am suppressing details here. But the bottom line is that if you now go back to this algorithm that we described earlier, so then that establishes our theorem. So the theorem, as I said, is that there's a deterministic algorithm for the global min cut problem that runs in time equal to polylog max flow calls. Okay, so I think I'll pause there. So because I've basically run out of time, and we'll start here tomorrow. And I'm happy to take any questions at this point.
So hi there, Malle. Will you tell us more details about this deterministic sparsification, or we should read somewhere else?
No, so I'm not going to. So this, I would, yeah, I welcome you to read the paper for this.
Okay.
I'm not going into it because in some sense, there's not a whole lot of novelty here. What's going on here is that we are just doing, it's a sort of case analysis of all these different cases just to show that you make sure that you straddle both sides.
But will you at least tell us about what this expanded, what is that called, decomposition is?
So the expanded decomposition
may not even know what this expanded decomposition.
Right. So this expanded decomposition is exactly obtaining the properties that I have written on this slide. So you, given any graph, you can partition it into components where each component has an expansion of phi. Phi is a parameter you can control. Mm-hmm. And the total number of edges between the components is like phi lambda times the total number of components.
Okay.
So it's exactly what's written here. How you obtain this in near linear time is complicated, and that's not even in our paper. We are just using a theorem from somewhere else.
Sure. Okay. Thanks.
I mean, one sort of structural way of thinking of this is that any graph looks like, at the right level of granularity, looks like a bunch of expanders. So a bunch of, let's say, random graphs, but which are connected by things that look very non-random, but the connections are few. So it's a very sparse connections. What's dense is inside these sets, but that dense part is very much like a random graph.
Okay. Okay. Thanks.
Other questions?
Yeah. Yeah. Okay. First of all, let me thank you on behalf of everybody, because I guess you cannot hear the claps. But yeah, more questions, if any. Okay, so if there are none, then I guess we close this session. And thanks, Demaloda, once again. We look forward to your second talk tomorrow. And
Thanks,
I
everyone.
guess we. Yeah.
Talk to you tomorrow.
Sorry.
No, I said thanks, everyone, and talk to you again tomorrow.
Yeah. Okay, so I guess we break for lunch now, and we meet again at 2 o'clock.
Yes, that is correct. So this was a wonderful starting session, and we hope to see you all again post lunch. Thank you.
Ma'am, can I end the meeting, ma'am?
Yes, and so the YouTube broadcast should also pause, and then we'll start back up maybe 5 minutes before. We'll be here for, say, 15 minutes or so before.
Yeah,
but
Zoom I will start at 1:45. and YouTube 5 minutes before the talk.
Sure. Thank you.